Somewhere, right now, there's a version of you that already watched this video. That version knows how it ends. That version knows every argument, every analogy, every moment where something clicks. And according to at least one serious line of physics, that version of you, the one who already finished watching, is out there somewhere, just as alive and just as present as the version of you sitting here at the beginning. That is what the math says. And the math is what we are going to walk through today, slowly, carefully, with nowhere to rush and nothing to skip. Before we get anywhere close to time machines or wormholes or spinning black holes, we have to start where every honest conversation about time travel has to start, with the deeply uncomfortable question of what time actually is. Because when most people imagine time travel, they imagine a clock, they imagine something ticking, they imagine time as a river that you are floating along. And the idea of time travel is that you somehow swim backward or launch yourself downstream. But that image, as natural as it feels, turns out to be almost completely wrong. And unpacking exactly how it is wrong is the thing that makes the rest of this conversation possible. So let us start there. Let us start with what time is, as best we currently understand it. For most of human history, people assumed time was universal, the same everywhere, ticking at the same rate, whether you were standing on the ground or flying through the sky, whether you were moving or sitting still, whether you were near a massive planet or floating in empty space. Isaac Newton said it outright in his work, that there exists an absolute, true, mathematical time which flows equally, with no relation to anything external. He wrote that in the 1680s. And for more than 200 years, nobody seriously argued with him, because nothing in everyday experience gave anyone a reason to. The problem came when people started really carefully thinking about light. In the late 1800s, physicists were doing experiments and realizing something confusing. Light always seemed to travel at the same speed no matter what. You would expect, if you were on a train moving toward a light source, that the light would seem to come at you faster, the way raindrops hit your windshield faster when you drive into them. But light did not behave that way. Light came at you at the same speed, regardless of how fast you were moving toward it or away from it. Every measurement, every experiment kept giving the same answer. The speed of light in a vacuum is always the same, about 300 million meters per second. This was not a rounding error. This was not a measurement mistake. This was the universe handing physicists a problem that did not fit inside the box they were working from. Albert Einstein, in 1905, decided to take that strangeness seriously. Instead of trying to explain it away, he asked, "What if this is just how it is? What if the speed of light is actually a fixed constant of the universe, something that never changes no matter who is measuring it or how fast they are moving?" And then he asked the follow-up question that changes everything. If that is true, what else has to change to make it possible? The answer he found was time. Time, Einstein showed, is not universal. It does not tick at the same rate for everyone. The rate at which time passes for you depends on how fast you are moving. The faster you move through space, the slower you move through time. These two things trade off against each other in a very precise mathematical relationship. And the reason the speed of light stays constant is because time bends to make it so. This is called time dilation, and it is not a metaphor. It is not a way of speaking. It is a measurable, tested, confirmed physical phenomenon. Time genuinely runs at different rates depending on how fast you are moving. The way to see why this has to be true is through a thought experiment that Einstein essentially gave us, though physicists have cleaned it up since. Imagine you have a clock made out of light, two mirrors facing each other, bouncing a single photon back and forth between them. Every time the photon hits one mirror, the clock ticks. Now, imagine you are holding this clock and someone else is watching you from a distance as you fly past them at a very high speed. From your perspective, the photon is going straight up and down between the mirrors. But from the perspective of the person watching you fly by, the photon has to travel a diagonal path, up and across and down and across, because the whole setup is moving horizontally, a longer path. Since light travels at a fixed speed, and the path is longer from the observer's perspective, the clock takes longer to tick from the observer's perspective. Your clock, in their frame of reference, is running slow. Now here is the part that matters. This is not an illusion. The observer is not mistaken. Time is genuinely running at different rates in the two situations. It is baked into the structure of space-time, and we have proved this directly. In 1971, physicists loaded extremely precise atomic clocks onto commercial airplanes and flew them around the world. When the planes landed and the clocks were compared to identical clocks that had stayed on the ground, the clocks on the planes had ticked slightly fewer times. They had aged slightly less. The difference was tiny, a fraction of a microsecond, but it was exactly the amount that special relativity predicted. We also see this in particle physics every single day. There are particles called muons that form when cosmic rays hit the upper atmosphere, around 15 kilometers above the surface of the Earth. Muons decay very quickly. If you created a muon sitting still in a lab, it would fall apart in about 2.2 microseconds. But muons created in the upper atmosphere, traveling down toward the Earth's surface at roughly 99.9% of the speed of light, managed to survive long enough to hit the ground. By all rights, they should decay before they even get halfway down. The reason they make it is that time is running slower for them because of their speed. From the muon's perspective, the journey takes microseconds. From ours, it takes much longer, and the muon survives to complete it. We have measured this thousands of times. The numbers always match the prediction. So we have established that moving fast through space slows you down through time. But Einstein did not stop there. About a decade later, he figured out something else. Mass does the same thing. Gravity, Einstein realized, is not a force that objects exert on each other across empty space the way Newton described it. Gravity is a curvature in the fabric of spacetime. Massive objects push down on spacetime the way a heavy ball pushes down on a rubber sheet. And anything near that curve, including light, including time, gets distorted by it. Near a massive object, time runs slower. The stronger the gravitational field, the more time slows down. This is called gravitational time dilation, and it is also completely confirmed. The GPS satellites orbiting Earth provide one of the best everyday examples. Those satellites are up in orbit where Earth's gravity is weaker than it is at the surface. Weaker gravity means time moves faster for them. Their clocks tick faster than clocks on the ground. At the same time, the satellites are also moving very fast, which by special relativity causes time to move slower for them. These two effects work in opposite directions, and engineers have to account for both of them with very precise corrections built into the satellite systems. If they did not, GPS coordinates would drift by about 11 kilometers per day. The fact that your phone navigation works at all is because we understand gravitational and velocity time dilation well enough to correct for them constantly. Near a black hole, where gravity is extraordinarily intense, this effect becomes extreme. If you could somehow hover just above the event horizon of a black hole, the boundary past which nothing escapes, time would be moving so slowly for you that years could pass out in the wider universe while you experienced only minutes. This is not science fiction. This is the same physics that makes your GPS work, just cranked up by an enormous factor. Now, both of those things together mean something very important. Speed slows time, and mass slows time. They mean that time travel into the future is not just theoretically possible, it is something we already do. Every time an astronaut goes to the International Space Station and comes back slightly younger than they would have been if they had stayed home, they have traveled forward through time by a tiny fraction of a second. The astronaut Scott Kelly spent roughly a year on the International Space Station. When he came back and the calculations were done across his full career in orbit, he was about 5 milliseconds younger than his twin brother Mark, who had stayed on the ground. Mark Kelly confirmed the gap himself publicly. 5 milliseconds is not something you can feel, but it is measurable. It is predicted exactly by the equations, and it is there. That gap, small as it is, means Scott Kelly's present moment arrived slightly further into the shared future than Mark's would have if they had both stayed together. Scale that up to a spacecraft traveling at a significant fraction of the speed of light, and the effect becomes enormous. This is the setup for what physicists call the twin paradox. The scenario goes like this. Two twins stand next to each other. One of them climbs into a spacecraft and accelerates to a very high speed, say 90% of the speed of light, flies out to a distant star, turns around and comes back. When they reunite, the twin who traveled has aged far less than the twin who stayed home. If the journey took 20 years by Earth's calendar, the traveling twin might only have experienced 8 or 9 years passing. They come back to an Earth where their sibling is much older and they are essentially younger than their own twin. This sounds like it should produce a contradiction. If motion is relative, and you can only ever talk about speed in relation to something else, then couldn't you argue that from the traveler's perspective, the Earth is the thing that moved, and therefore the Earth twin should age less? Why does the traveling twin come back younger? The resolution is that the situation is not symmetric. The traveling twin had to turn around. To do that, they had to decelerate, reverse direction, and accelerate again. That acceleration is a physical event that only happens to one of them. The traveling twin changed reference frames and changed their state of motion in a way the Earth twin did not. This breaks the symmetry, and relativity tells us precisely how. The traveling twin always comes back younger by a calculable amount. The numbers have been verified in experiments with atomic clocks flown on aircraft and checked against ground clocks. The physics is settled. What this means is that if you wanted to travel into the future, you essentially know how to do it in principle. You build a spacecraft capable of reaching near light speed. You take a trip and you come back. The longer the trip, the further into the future you arrive. Go fast enough, far enough, and you could theoretically travel thousands of years into Earth's future while experiencing only a few years aboard the ship. This is forward time travel, and general and special relativity make it not just possible, but mandatory. You cannot avoid it. The harder problem, the one that fills papers and keeps physicists awake, is going the other direction. To understand why traveling backward through time is so much stranger and more difficult, we need to talk about how physicists actually picture space and time together. Einstein showed us that space and time are not separate things. They are woven together into a single fabric called spacetime. You can think of it as a four-dimensional object where three of the dimensions are the spatial ones you are used to: up, down, left, right, forward, back, and the fourth is time. Every event in the history of the universe is a single point in this four-dimensional block. Your birth is one point in the block. Your death is another point. Every moment of your life is a point, and the sequence of all those points traces out a path through space-time called a world line. In this picture, the universe does not unfold over time. The universe simply is, all of it at once, past, present, and future, laid out as a static four-dimensional object. Physicists sometimes call this the block universe, and while it sounds philosophical, it follows pretty directly from the mathematics of special relativity. Different observers, moving at different speeds, will disagree about which events are simultaneous. Events that look like they happen at the same time for one observer will look like they happen at different times for another observer moving relative to them. This is also confirmed. It is called relativity of simultaneity. And once you accept that different observers can have different nows, the idea that there is one single universal present moment starts to fall apart. The most natural interpretation the math offers is that all moments exist equally, laid out in the block. This is where the idea of time travel gets its first genuine foothold, theoretically speaking. If all of space-time is laid out in a block, then moving through time is similar in principle to moving through space. You are always at some location in the block, moving along your world line. The question becomes, could you take a path through the block that bends back on itself? Could your world line curve around in such a way that you end up at an earlier point in the block than where you started? In physics, such a path has a name. It is called a closed time-like curve. A closed time-like curve is a path through space-time that loops back to its own starting point. If you are traveling along a closed time-like curve, you pass through space and time in a way that eventually brings you back to the exact same location in space-time where you began, the same place, the same moment. You have traveled into your own past. The extraordinary thing, the thing that drives a lot of the subsequent physics, is that closed time-like curves are not automatically ruled out by general relativity. They appear as solutions to Einstein's equations. The question is not whether they are mathematically possible. Several different types of space-time geometry permit them. The question is whether the universe actually allows them to form in a physical way. The first person to show that Einstein's equations could produce a universe with closed time-like curves was not a physicist. He was a mathematician. His name was Kurt Gödel. Gödel is mostly remembered for his incompleteness theorems, which showed certain inescapable limits in formal mathematical systems, but he was also a close friend of Einstein's at the Institute for Advanced Study in Princeton in the 1940s. As a kind of intellectual gift for Einstein's 70th birthday in 1949, Gödel worked out a solution to Einstein's field equations that described a rotating universe. Not a rotating planet, not a rotating galaxy, a universe that is itself spinning as a whole. In this rotating universe, Gödel showed space-time gets dragged around by the rotation in a way that creates closed time-like curves everywhere. In a Gödel universe, you could, in principle, take a long trip through space and come back before you left. You would not need any special machine. You would just need to follow a path through a universe that is structured the right way. Now, the universe we live in does not appear to be rotating in this manner. Observations suggest it is not a Gödel universe. So, this particular example does not immediately hand us a time machine, but What Gödel showed is something important and uncomfortable. The equations that describe our universe, the same equations that predict black holes and gravitational waves and the expansion of the cosmos, equations that have been confirmed to extraordinary precision. Those equations have solutions in which time travel is possible. The door, mathematically, is not locked. Once Gödel kicked that door open, physicists started looking around for other solutions to Einstein's equations that might produce closed time-like curves, and they found several. One of the most discussed mechanisms involves a structure called a wormhole. A wormhole is a hypothetical passage through space-time. Imagine you take a sheet of paper and fold it so that two parts of it are close together. Then poke a hole through both layers and connect them with a tube. Instead of traveling across the surface of the paper from one point to another, you can go through the tube and emerge at the other point much more quickly. A wormhole works the same way in space-time, connecting two distant regions, two different locations in space, two different points in time, through a shortcut. The mathematical groundwork for wormholes goes back to Einstein himself, along with his collaborator, Nathan Rosen. In 1935, they were working through solutions to the equations of general relativity and found that a black hole, when you do the full mathematical treatment, does not just have a region of extreme gravity pulling things in, it also has a sort of mirror image on the other side, what we might call a white hole, which would push things out. Connecting these two mouths is a narrow tube through space-time. This Einstein-Rosen bridge is mathematically there in the solution. It is woven into the geometry. The problem is that the original Einstein-Rosen bridge is not traversable. The tunnel pinches off and collapses faster than any object could travel through it. To use it, you would need to move faster than light, which is not allowed. For decades, wormholes were a mathematical curiosity, an interesting feature of the equations that did not seem to have any physical relevance. Then, in 1988, physicist Kip Thorne and his colleague Michael Morris changed the conversation. They were working on a paper inspired, improbably, by a phone call with the science communicator Carl Sagan, who was writing a novel, the book that became Contact, and wanted to know if wormholes could be made to work. Thorne and Morris decided to take the question seriously, and they worked backward. Instead of starting with a physical setup and asking what geometry it produces, they started with a geometry, a traversable wormhole, one that a person could actually travel through, and asked what physical conditions would be necessary to maintain it. What they found is that keeping a wormhole open requires something called exotic matter. Exotic matter is not just some unusual material. It is matter with a property that no confirmed material in everyday experience has: negative energy density. Ordinary matter has positive energy. It pulls space-time inward, creating normal gravity. To keep a wormhole from collapsing, to push the throat open against the natural tendency of space-time to pinch it shut, you need something that does the opposite, something that has a repulsive effect on space-time, something with negative energy. This sounds like it should rule wormholes out completely, and many physicists believe it does. But the situation is more nuanced than a clean impossibility. There is a phenomenon in quantum mechanics called the Casimir effect. If you take two metal plates and hold them extremely close together in a vacuum with no air, no anything between them, they experience a tiny attractive force pulling them together. The reason is quantum. The vacuum between the plates cannot support all the possible energy states that exist in open space. Some wavelengths of quantum fluctuations are excluded from the narrow gap. This means the vacuum between the plates has slightly less energy than the vacuum outside them, which means the energy density in the gap is negative relative to the energy density outside. This is not ordinary negative energy in the dramatic sci-fi sense. It is a subtle quantum effect. The magnitude is extraordinarily small, and it works only on scales smaller than the distance between atoms. But it shows that negative energy density is not prohibited by quantum mechanics. It can exist, at least in principle. The question is whether it could ever be produced or controlled at the scale needed to stabilize a wormhole. The honest answer is that we do not know. The amount of exotic matter required to hold open even a tiny wormhole, by most estimates, is astronomical, comparable to the mass energy of a planet or a star with a negative sign. Even optimistic revisions of the calculations leave the required quantities far beyond anything we could imagine producing. But the physics does not say it is impossible. It says it is very hard, and we do not yet know how. Now, here is where wormholes connect to time travel specifically, and where Kip Thorne's work becomes particularly vivid. Suppose you had a traversable wormhole, two mouths connected by a tunnel through space-time. At first, both mouths exist at the same moment in time. If you jump into one mouth, you come out the other in a different location in space, but at the same time, no time travel yet. Just a spatial shortcut. But now, take one of the mouths and accelerate it to a very high speed. Remember what we established earlier. Moving fast through space slows you down through time. The accelerated mouth ages more slowly. After some period of time, from the perspective of someone outside, the accelerated mouth has experienced far less time than the stationary mouth. The interior of the wormhole connects them, but now the two mouths are at different points in time as well as space. If you jump into the mouth that has been aging more slowly, you come out the stationary mouth at an earlier point in time. You have gone backward. Alternatively, you could hold one mouth near a massive object and leave the other in empty space. The mouth near the mass ages more slowly due to gravitational time dilation. After a while, you have the same setup, two mouths that are at different moments in time. This is the wormhole time machine, as Thorne and his collaborators described it. The time gap between the two mouths cannot be made larger than the time since you created the wormhole. You cannot use it to go back before it was built, but Within that window, it would let you send something or someone back in time. The moment you use a wormhole like this to send anything back in time, you have created a closed time-like curve. Something traveling through the wormhole can potentially meet itself on the other side, interact with its own past, and create a loop. And this is where the physics gets genuinely difficult. Because a closed time-like curve is not just a strange route through space-time. It is a logical challenge. If you can send a signal or an object back through time, you can potentially change the conditions that led to that signal being sent, which might mean the signal is never sent, which means the change never happened, which means everything that led to the change proceeds as it originally would have, which means the signal gets sent again, around and around. This is the structure of the paradoxes that cluster around backward time travel, and they are serious enough that they have driven physicists to propose several different ways the universe might handle them. The most viscerally famous of these paradoxes is the grandfather paradox. You travel back in time, and for whatever reason, you prevent your own grandparents from meeting. Your parent is never born. You are never born, which means you never travel back in time, which means your grandparents do meet after all, which means you are born, which means you travel back and around we go. The grandfather paradox feels like a proof that time travel into the past is simply impossible, that the universe cannot allow it because it leads to logical contradictions that have no resolution. And many physicists take exactly that position. But there are others who have thought carefully about what mechanisms might prevent the paradox from arising in the first place. One approach was developed by Russian astrophysicist Igor Novikov. In the 1980s, Novikov proposed what is now called the Novikov self-consistency principle. The idea is this: if a closed time-like curve exists, then the only events that can occur along that curve are events that are globally consistent. The laws of physics do not allow anything to happen that would create a contradiction. The probability of any event that would produce a paradox is exactly zero. Not just very small, but precisely zero. It cannot happen. What this means in practical terms is that if you travel back in time intending to kill your grandfather, something will always stop you. Not a mysterious force, not a time police, not a cosmic rule enforcer, just ordinary physics conspiring in every possible way to make your attempt fail. You trip, the gun jams, you get lost, you have a change of heart, whatever it takes. And the reason is not that the universe is pulling strings. The reason is that any timeline in which you succeeded would be a logically inconsistent timeline, and logically inconsistent timelines are not solutions to the equations. They do not exist. Only consistent timelines exist. The Novikov principle produces a very specific kind of time travel story. In a Novikov consistent universe, everything you do when you travel to the past was already part of what happened. History does not have a before and after where you intervened. History was always the version that included your intervention. You cannot change anything because what you do was always what happened. The past, in this picture, is fixed and unchangeable. You are just finally showing up to play your predetermined role in it. This resolution has an elegant quality to it, but it comes with its own deeply unsettling implications. If the past is completely fixed and nothing can be changed, then the future must be fixed as well. Every decision you make, every action you take was already determined. The only events that happen are the ones that are consistent with the entire history of the universe laid out in its four-dimensional block. Free will, in any meaningful sense, becomes hard to locate in this picture. There is a second paradox that sits alongside the grandfather paradox and is somewhat less discussed, but in some ways stranger. It is called the bootstrap paradox, and it is not about preventing your own existence. It is about creating information out of nothing. The scenario works like this. Suppose you are a physicist, and one day a mysterious stranger visits you and gives you a set of equations, a complete theory of time travel. You study those equations, build the time machine they describe, travel back in time, and find your younger self. You hand over the equations and disappear. Now, where did the equations come from? You got them from the stranger. The stranger was your future self. Your future self got them by receiving them from their own stranger, which was their future self. Somewhere in this loop, nobody ever derived the equations from scratch. Nobody sat down and worked them out from first principles. The information has no origin. It exists in a closed loop, each copy of it caused by a previous copy of it, with no beginning point and no source. The equations simply are cycling through time, apparently conjured from nothing. The same structure can apply to physical objects, not just information. A time traveler brings a book to the past. Someone in the past reads the book, publishes it, and the published version is eventually the one the time traveler takes back to the past. Where did the book's contents come from? Who wrote it? Nowhere and nobody. If you follow the loop, this is a paradox without the logical contradiction of the grandfather paradox. Nothing is being prevented from existing, but it violates something that feels like a physical principle. Energy and information seem to appear from nowhere. Some physicists consider bootstrap scenarios acceptable under the Novikov principle because they are at least internally consistent. Others argue that they represent a different kind of problem. They tell you that in a universe with time travel, you can generate information without any source, which feels like it should violate something deep about physics, even if we cannot immediately say which law it breaks. Novikov's self-consistency principle is one answer to the paradox problem. The other major answer involves parallel universes. The many worlds interpretation of quantum mechanics developed by physicist Hugh Everett in the 1950s proposes that when a quantum event occurs with multiple possible outcomes, the universe does not randomly pick one outcome and discard the others. Instead, the universe branches. Every possible outcome occurs, each in its own separate branch of reality. These branches do not interact with each other after the split. They all exist simultaneously, running in parallel. If you apply this idea to time travel, the paradoxes dissolve in a different way. When you travel back in time and do something that would create a contradiction, you are not changing your own past. You are entering a new branch, a parallel timeline. Your actions in that branch create whatever they create, including potentially preventing your grandparents from meeting, but that does not affect the branch you came from. In your original timeline, you still exist, you still travel back, and somewhere in the multiverse, there is now a branch where your grandparents never met, and the version of you they might have produced was never born. But you, the traveler, are fine. You just arrived in what is effectively a different universe. This is a cleaner resolution to the logical paradoxes, but it creates a different set of conceptual problems. The parallel timelines multiply endlessly. Every time travel event creates new branches. The question of what you are in this picture becomes complicated. The many worlds interpretation is also famously controversial in its own right. Physicists are genuinely divided about whether it is the correct description of quantum mechanics, even setting aside the time travel question. But it remains one of the leading frameworks for resolving time travel paradoxes, and it has been extended by physicist David Deutsch into a detailed model of how closed time-like curves could work without contradiction in quantum mechanics. Deutsch's model suggests that if a quantum system travels along a closed time-like curve, it does not have to produce a single self-consistent history. Instead, the system evolves into a mixed state, a probabilistic superposition that satisfies a consistency condition in terms of the overall probability distribution, rather than requiring each individual history to be consistent on its own. This allows quantum computers traveling back through time to perform certain calculations that would be impossible otherwise. It is a way of making the math work without requiring either Novikov-style predetermined fate or a strict branching of timelines. Moving away from wormholes and into other mechanisms, let us spend some time with a different route that appears in general relativity, the rotating black hole. A standard black hole, the kind formed when a sufficiently massive star collapses at the end of its life, has a singularity at its center. A singularity is where the mathematics breaks down, where quantities like density and curvature go to infinity. Anything falling into such a black hole eventually reaches the singularity, and there the story ends. The singularity is not a place inside the black hole so much as a moment in time, a future moment that you cannot avoid once you cross the event horizon, the way you cannot avoid Tuesday once Monday is over. In 1963, mathematician Roy Kerr found a solution to Einstein's equations describing a rotating black hole, and this changed the picture in a surprising way. A massive star that collapses is almost certainly spinning. Stars rotate, and when they collapse, conservation of angular momentum makes them spin faster, the way an ice skater pulls in their arms to spin faster. The question of what a rotating black hole looks like is therefore not a purely academic exercise. It is probably the realistic description of most actual black holes in the universe. A Kerr black hole, a rotating black hole, does not have a point-like singularity at its center. Because it is spinning, centrifugal effects spread the singularity into a ring singularity in the equatorial plane of the black hole's rotation. And this creates a geometric possibility that the non-rotating black hole does not have. If you approach a Kerr black hole and thread through the ring, staying clear of the ring itself, you do not hit the singularity. The ring is like a portal. Pass through the center of the ring, and the mathematics of the Kerr metric suggests you could emerge in a region of spacetime with what looks like a time coordinate pointing in the wrong direction, a region where closed time-like curves are present, following certain trajectories through and around a Kerr black hole. The geometry permits paths that loop back in time. You could, in principle, circle the ring singularity multiple times and emerge not just in a different region of space, but in an earlier period of time. Now, the practical problems here are staggering. Getting anywhere near the interior of a Kerr black hole requires surviving the trip in, which, for any realistic stellar mass black hole, would involve tidal forces that would shred any conceivable spacecraft and any conceivable human occupant long before they reached the relevant geometry. There are theoretical proposals involving supermassive black holes, the kind found at the centers of galaxies, with masses millions or billions of times that of the Sun, where the tidal forces at the event horizon are much gentler, but even then you are going in, you are not obviously getting out. The other issue is that the interior of the Kerr metric, the region inside the inner horizon where the interesting geometry lives, is thought to be unstable. Small perturbations, like the gravitational effect of anything actually falling in, may cause the geometry to collapse into something different before the exotic features can be used. The Kerr black hole as a time machine is probably a mathematical idealization that does not survive contact with physical reality. But it remains one of the places in the equations where backward time travel appears, and it was not put there by hand. It came out of a solution that describes something we believe actually exists in the universe. Another mechanism from general relativity that permits closed time-like curves was proposed by physicist Frank Tipler in 1974. Tipler was working with an older solution to Einstein's equations found by Willem van Stockum in the 1930s, which described what happens when you have an infinitely long, massive, rapidly rotating cylinder. Van Stockum's solution showed that a sufficiently massive sufficiently rapidly rotating infinite cylinder drags space-time around it so severely that the direction of time in the rotating region becomes warped. Tipler showed that this warping produces closed time-like curves near the cylinder. If you flew a spacecraft along a helical path around such a cylinder, starting and ending at the same point in space, you could end up at an earlier point in time. The immediate problem with the Tipler cylinder is that it needs to be infinite in length. A finite cylinder does not produce closed time-like curves. You can see this from Hawking's later work, which showed more broadly that creating a time machine in a finite region of space without exotic matter is not possible within general relativity. The infinite length requirement means the Tipler cylinder, as described, would require an infinite amount of mass energy to build, which is to say, it cannot be built, not because of some engineering limitation we might one day overcome, but because the universe does not contain infinite amounts of matter. Still, the Tipler cylinder adds to the picture of how closed time-like curves emerge from rotating spacetimes. There seems to be something about rotation in the Gödel universe, in the Kerr black hole, in the Tipler cylinder, that allows spacetime to be warped in ways that permit time loops. This is not a coincidence. Angular momentum has a special relationship with the curvature of space-time, and there is a deeper structure here that is still being worked out. In the 1990s, a physicist named J. Richard Gott proposed yet another mechanism, this one based on cosmic strings. Cosmic strings are hypothetical objects, extremely thin, extremely dense filaments of energy that may have formed in the very early universe as a kind of defect in the fabric of spacetime, the way bubbles form in cooling water or cracks form in cooling metal. If cosmic strings exist, they would be essentially one-dimensional, essentially zero width, but potentially enormous length, stretching across cosmological distances, and they would be extraordinarily dense. A single centimeter of cosmic string would contain roughly the same mass as a mountain. Gott showed that if you had two such cosmic strings moving past each other at very high speed, the space-time geometry around the region where they pass each other would be distorted in a way that creates closed time-like curves. You could circle around both strings along a precisely chosen path and end up back where you started, in both space and time. No cosmic string has ever been observed. Whether they exist at all is an open question. And even if they did, no one has any idea how you would arrange two of them to pass each other at the required speeds. But Gott's solution, like the others, is a legitimate answer to Einstein's equations. It shows that the physics does not rule out backward time travel, even through this mechanism. Now, we should spend some time with the most dramatic proposal of all, the Alcubierre drive. In 1994, Mexican theoretical physicist Miguel Alcubierre was sitting at his desk, probably having a very good day, and he found a solution to Einstein's field equations. that describes a warp bubble. The idea works like this. Take a region of flat space-time, a bubble of space, and allow space itself to contract in front of the bubble and expand behind it. The bubble rides this wave of contracting and expanding space-time. Inside the bubble, nothing moves faster than light locally. The bubble itself, carried by the contraction and expansion of space, can move at any speed, including faster than light. This is the same basic idea as the expansion of the universe. The universe itself is expanding, and distant galaxies are receding from us faster than light, not because they are moving through space faster than light, but because the space between us and them is growing. They are at rest in their local patch of space. The space just keeps getting created between us. Alcubierre's drive does something similar, but directionally. The connection to time travel is that anything capable of moving faster than light in relativistic physics can also be used to travel backward in time. The argument involves reference frames. In some frames of reference, a superluminal signal sent from point A to point B actually arrives at B before it was sent from A. If you can send signals faster than light, you can construct scenarios where you can send a message to your own past. The details depend on exactly how the superluminal motion works, but the general connection is tight enough that physicists often say that any mechanism that allows faster than light travel also allows time travel. Alcubierre's solution is completely consistent with general relativity mathematically. The problem, again, is exotic matter. To contract space in front of the bubble, you need a region of space-time with negative energy density. You need something pushing back against the normal tendency of space, and the amounts required are extraordinary. Early estimates suggested you would need a quantity of exotic matter with negative energy equivalent to the mass energy of Jupiter. Later calculations revised this somewhat downward by modifying the shape of the bubble, but even optimistic versions of the calculation still require negative energy at scales completely beyond our current understanding of how to produce or control it. There is also a control problem. To steer the warp bubble, you need to send signals into the region of contracted space at the front of the bubble. But the front of the bubble is contracted, compressed. You cannot send a signal into it from inside without going faster than light, which defeats the point. In its simplest form, a warp bubble, once started, cannot be steered or stopped from inside. You would need to set up your path in advance, using structures placed along your route before you departed. And there is one more problem. A warp bubble moving through space would accumulate particles from the vacuum, quantum fluctuations that get swept up at the front and then released in an intense burst when the bubble stops. The people inside might not survive the arrival. None of this is reason to dismiss the Alcubierre drive as a topic of study. Physicists continue to work on variations of the geometry, trying to find versions that require less exotic matter or have better properties. But at this stage, it is a mathematical solution that tells us something about the structure of general relativity rather than a blueprint for an engineering project. We have now walked through 6 distinct mechanisms that general relativity offers for closed time-like curves. The Gödel rotating universe, wormholes with exotic matter, Kerr rotating black holes, the Tipler cylinder, GOTS, cosmic strings, and the Alcubierre warp bubble. Every one of them is a genuine solution to Einstein's field equations. The math is there. What they all share is a requirement for either exotic matter with negative energy density, or structures that are infinite in extent, or conditions so extreme that no known process in the universe could produce them. And every single one of them runs into the same opponent, Stephen Hawking. In 1992, Hawking published a paper that many physicists consider the most important word on this subject. He proposed what he called the chronology protection conjecture. Hawking's argument went like this: consider what happens when you try to form a closed time-like curve. As you approach the moment where the curve would close, the moment where a time machine would first become operational, virtual particles from quantum mechanics start circling the loop. Quantum mechanics tells us that in any region of spacetime, virtual particle-antiparticle pairs are constantly popping in and out of existence. They borrow energy from the vacuum, exist for the briefest moment, and then annihilate each other. Near a closed time-like curve, these virtual particles have a special problem. They can potentially travel around the loop and meet themselves. In fact, they can travel around the loop and pile up. Each circuit adds another copy of the particle to the path, and these copies add up. A single virtual particle circling a time loop becomes many copies of itself piling on top of each other, and each copy contributes to the energy density of the region. As the loop gets closer and closer to closing, this pileup becomes more and more intense. The energy density in the region around the forming closed time-like curve grows without bound. What Hawking argued is that this runaway buildup of energy density would destroy whatever mechanism was trying to form the closed time-like curve before it could actually close. The quantum vacuum itself acts as a kind of immune system for causality, releasing enough energy to collapse any time machine before it becomes operational. Hawking, with a characteristic mix of precision and wit, called this hypothetical mechanism the chronology protection agency. He said, "It seemed that there is a chronology protection agency which prevents the appearance of closed time-like curves and so makes the universe safe for historians." He was not entirely joking, but he was honest about the limits of the argument. The calculation that shows the energy density piling up is done using what physicists call semi-classical gravity, a framework that treats spacetime as classical, following general relativity, while treating the particles in it as quantum. This is a valid approximation in many situations, but near Planck scale energies and distances, the scales at which quantum gravity becomes important, semi-classical gravity breaks down. You need a complete theory of quantum gravity to know what really happens there. We do not have a complete theory of quantum gravity. String theory and loop quantum gravity are leading candidates, but neither is fully developed or confirmed. The chronology protection conjecture rests on a calculation that is valid in a regime that breaks down precisely at the moment when it matters most. Hawking himself acknowledged this. His conjecture is strongly motivated, deeply plausible, and remains unproven because the proof would require physics we do not yet have. This is not a minor footnote. The chronology protection conjecture, if true, would definitively close off backward time travel in our universe without needing to appeal to paradoxes or engineering difficulties. The universe would simply prevent it at a deep physical level. But if quantum gravity somehow allows the energy density to be tamed, if there is a mechanism that prevents the blowup, then the protection conjecture fails and the door stays open. This is where the physics actually stands today. We cannot definitively rule out backward time travel. We have very strong reasons to think it is prevented, but those reasons rest on physics we have not yet fully worked out. Let us stop for a moment and look at what we have covered, not to summarize it, but to follow the thread that connects all of it. We started with the observation that time runs at different rates for different observers. This came from Einstein's work and has been confirmed over and over. From there, the picture emerged that time is a dimension, that spacetime is a unified four-dimensional structure, and that all of it, past, present, and future, may exist in some sense simultaneously in the block universe. From that picture, it followed that traveling backward through time is conceivable in principle. It just requires finding a path through the block that loops back on itself. General relativity, which is the best theory we have of how mass and energy shape spacetime, provides several solutions that contain such loops. But each of those solutions either requires exotic matter, which we have not found a way to produce, or infinite structures which cannot be built, or conditions so extreme that a time machine built that way would destroy itself or anyone who tried to use it. Every time someone finds a mathematical route through this problem, the universe seems to put up another obstacle. Exotic matter may be possible in quantum mechanics, not practically producible at scale. Wormholes, valid solutions, but they collapse without exotic matter, and quantum effects may destroy them when you try to use them as time machines. Rotating black holes contain the right geometry, but the interior is unstable, and you cannot survive the approach to the relevant region in any realistic scenario. The chronology protection conjecture, not proven, but strongly suggesting that quantum effects will always prevent closed time-like curves from forming. It feels like the universe is saying something. The question is what? One reading of this pattern is that backward time travel genuinely is impossible, and we are watching physicists gradually close off every apparent loophole, one by one. Each new mechanism for time travel turns out to be either physically unrealizable or self-defeating. The universe allows the mathematics to flirt with the possibility while always managing to prevent it in practice. A different reading is that we are hitting the limits of our current theories rather than the limits of nature. The chronology protection conjecture, specifically, is not a theorem, it is a conjecture. It rests on semi-classical gravity, which everyone agrees is not the complete story. A complete theory of quantum gravity might overturn it, or it might confirm it, we do not know. And there are physicists who have argued carefully and in published work that under some conditions the chronology protection could fail, or that certain quantum effects might actually stabilize rather than destroy a time machine's Cauchy horizon. It is also worth noting that every one of the mechanisms we discussed for backward time travel is related to the broader structure of general relativity in ways that seem extremely unlikely to be completely disconnected from physical reality. Rotating black holes are not exotic speculations. We believe they are the majority of black holes that exist. Their interior geometry, containing closed, time-like curves, is part of the solution, not a separate add-on. Wormholes emerge from the same mathematics as black holes. Exotic matter with negative energy density exists in small amounts in the Casimir effect. These are not random fantasies. They are features of our best theory of gravity and space-time. It is worth saying something about what time travel into the past would actually look like if it were possible, before we lose the thread entirely to the abstract. In a Novikov consistent universe, one where only self-consistent histories can occur, traveling to the past would mean arriving at a moment that was always going to have you in it. You would not be able to change anything that has not already been changed. If you traveled back and tried to leave a message for yourself, you would find the message was already there, waiting for you, having always been there in historical records. If you went back to prevent an event, you would find yourself somehow prevented from preventing it. The past would feel, to you, completely ordinary. It would just be the world as it was. But your presence there would be woven into the causal fabric of the history you came from. In a many worlds picture, things would look different. You would step out into a world that looks exactly like your past, but it would be a branch, a parallel timeline. You could do whatever you wanted, change whatever you could change, kill whoever you tried to kill, and the results would unfold in that branch. Your original timeline would be unaffected. You could never get back to your original timeline because that would require a second time travel event going forward, and the forward direction in your new branch would be different from the forward direction in your original branch. In either case, the experience of time travel would be far less dramatic than popular imagination suggests. No rushing tornado of special effects. You would simply be somewhere and you would check the date, and the date would be earlier than when you left. The buildings would look different. People would be dressed differently. Everything around you would be perfectly ordinary to the people in it. The only person experiencing anything unusual would be you. Now, there is a question that comes up whenever this topic is discussed seriously. If backward time travel is possible, where are the time travelers? Hawking himself pointed to this as evidence for the chronology protection conjecture. We have no confirmed records of visitors from the future. No one has shown up to warn us about upcoming disasters. No one has placed a bet on a sporting event using tomorrow's results. The absence of time travelers in recorded history is at least consistent with the hypothesis that backward time travel never becomes possible. The many worlds picture offers a response to this. If time travel creates branches, then time travelers from our future go to different branches when they arrive. They are not in our timeline anymore. Their interventions change their destination branch, not ours. So we would not expect to see them here even if time travel becomes common in the future. The Novikov picture offers a different response. If only self-consistent histories are possible, then the events that time travelers participated in have always been part of the historical record, but we might not recognize them as time travelers. Someone who appeared mysteriously in a village 300 years ago and left without explanation might have been a time traveler, but we have no way to know. The historical record does not usually flag that kind of thing. There is also a more simple logistical argument. Even if backward time travel becomes possible at some point in the future, the mechanism may only allow travel back to the moment the time machine was first switched on, not further. A wormhole time machine, as described by Thorne, can only be used to go back to the moment the wormhole was first created and one end was accelerated. You cannot go back before the machine existed. If the first time machine is built in, say, the 23rd century, then the earliest anyone could travel to using that machine is the 23rd century. Nobody from the future can visit us now because the machine has not been built yet. Let us also spend some time with what happens to our understanding of causality, the relationship between cause and effect in a universe with time travel. Causality, as we normally understand it, means that causes always come before their effects. You throw a ball and then the window breaks. You say something hurtful and then the other person feels hurt. The cause happens and then the effect happens in that order. Every event can be traced back to a prior cause, and that cause to a prior cause, and so on, stretching back through time. In a universe with close time-like curves, this chain can form loops. An event can be its own cause. The time traveler goes back and causes an event that eventually causes them to travel back in the first place. The event and the cause are the same thing, viewed from different points on the loop. This is not a problem in the same way that the grandfather paradox is. Nothing contradicts itself in the bootstrap paradox. But it breaks something that feels deeply important about physics. The idea that you can always ask where something came from and get a coherent answer that traces back to initial conditions. Some physicists argue that bootstrap-style causation, information, or objects that exist in closed loops without any external origin would violate the second law of thermodynamics. The second law says that entropy, roughly speaking, disorder, tends to increase over time in an isolated system. A closed causal loop is a system with no net change in entropy over the course of the loop. Whether this is truly a violation or just an extreme edge case is debated. Others point to quantum mechanics, which is in some ways already comfortable with non-standard causation. The transactional interpretation of quantum mechanics, for instance, involves particles sending influence both forward and backward in time simultaneously, with a kind of handshake between a future absorber and a past emitter determining quantum outcomes. Retrocausation, the idea that future events can influence the present, has been a subject of serious discussion in quantum foundations for decades. It has not been confirmed, but it is not dismissed either. Some physicists believe that a complete theory of quantum gravity will require a completely different understanding of time's direction, one in which forward and backward are on more equal footing than our everyday experience suggests. The arrow of time, the fact that we perceive time as moving in one direction from past to future, is itself one of physics' unresolved mysteries. At the level of individual particles, the laws of physics are almost entirely time-symmetric. The equations describing two electrons interacting work equally well if you reverse the direction of time. Run the film of subatomic interactions backward, and in most cases you cannot tell the difference. Even the weak nuclear force, which is the one exception at the quantum level, only breaks time symmetry very slightly and in very specific circumstances. At the microscopic level, there is almost no arrow, but at the macroscopic level, there is an enormous arrow. You can scramble an egg, but not unscramble it. You can mix cream into coffee, but you cannot spontaneously unmix it. A glass falls off a table and shatters into 100 pieces. You never see 100 pieces spontaneously leap off the floor and reassemble into a glass. These processes are overwhelmingly one-directional in time, and we experience this as the flow of time. The arrow of time at the macroscopic level comes from entropy, from the fact that there are vastly more ways for a system to be disordered than ordered, so disordering is overwhelmingly more probable. But this statistical argument just pushes the question back. Why was entropy so low at the beginning? Why did the universe start in a state of extreme order, the Big Bang, from which entropy has been growing ever since? This is an open question in cosmology. Some proposals involve the large-scale structure of the universe, or the nature of the initial state before the Big Bang, or the possibility that the universe is much larger than the observable portion, and we happen to live in a low-entropy region of a larger, high-entropy whole. What is relevant for time travel is this: the arrow of time is not in the deep laws themselves, it is in the initial conditions. A universe with a different arrow of time would look the same at the particle level, but would have entropy flowing in the other direction, with what we would call the future having lower entropy than what we would call the past. Whether a time machine could create a local region where entropy flows backward, a region that effectively has a reversed arrow of time, is an interesting question without a clean answer. One last thread worth pulling is the relationship between quantum mechanics and time travel that goes beyond the many worlds interpretation. In quantum mechanics, particles do not have definite positions or momenta until they are measured. Before measurement, they exist in a superposition of multiple possible states simultaneously. When you measure, you get one definite result, and the probability of each possible result is determined by the wave function. This has an interesting interaction with closed time-like curves. Suppose a quantum particle travels along a closed time-like curve and interacts with its past self. Before the interaction, the particle is in some quantum state. After the interaction, which is before the interaction, because time is looped, the particle is in a possibly different state. This state then evolves and eventually arrives at the interaction point as the original past self. You need the particle state before and after the interaction to be consistent with each other through this loop. In classical physics, this is a Novikov consistency condition. The particle state is the same before and after. In quantum physics, things are richer. You can have a situation where no single definite quantum state is self-consistent around the loop, but a mixed state, a probability distribution over multiple quantum states, is self-consistent. Deutsch explored this in his 1991 paper and showed that quantum mechanics on closed time-like curves can produce behavior that is completely impossible in ordinary quantum mechanics. A quantum computer on a CTC could, in principle, solve problems that are computationally intractable in the absence of time travel. It could distinguish between quantum states that are in principle indistinguishable without a time loop. It could violate certain hard limits of ordinary quantum information theory. This is extraordinary if it turns out to be correct. It means that if closed time-like curves exist anywhere in the universe, even at microscopic scales, even for particles rather than people, they would leave computational signatures. The ability to solve certain classes of problems would be enhanced in ways that standard quantum mechanics cannot account for. Whether this is observable and whether the universe's apparent hostility to closed time-like curves prevents this even at the quantum scale is an active area of research. Pulling all of this together, what can we actually say about time travel? Forward time travel is not a speculation. It is an ongoing fact of physics. Every fast-moving particle in a collider, every astronaut in orbit, every muon falling through the atmosphere is time traveling forward relative to observers at rest. The mechanism is understood, it is quantitative, it is confirmed. Scale it up with sufficient technology, and there is nothing in physics preventing a person from traveling thousands of years into the future of the universe, while experiencing only a few years of personal time. Backward time travel is a much harder question. The mathematics of general relativity genuinely allows it in specific geometric configurations. The laws of physics, as currently understood, do not conclusively rule it out. What they do is put enormous obstacles in front of every mechanism we have found. Obstacles that may or may not be surmountable, depending on physics we have not yet developed. The most honest statement is this: backward time travel sits at the exact boundary of what our current theories can say. We are asking questions that require a theory of quantum gravity, which we do not have. We are asking about conditions, near singularities, near Cauchy horizons, at Planck scale energies, where our current tools break down. The answer to whether backward time travel is physically possible may require the same theoretical revolution that general relativity was relative to Newton, or that quantum mechanics was relative to classical physics. We are not at the end of physics. We are not even close. What we have, instead, is a collection of mathematical structures that are far richer and stranger than they had any reason to be. Rotating black holes that contain geometric regions where time loops back, quantum mechanics that produces non-classical results on closed time-like curves, solutions to field equations that describe traversable shortcuts through space-time. None of these were discovered by looking for time machines. All of them came out of following the mathematics of our best theories to their logical conclusions. That the same mathematics that predicts the orbit of Mercury to extraordinary precision and the existence of gravitational waves that were confirmed a century after Einstein predicted them, and the specific spectrum of light from distant stars, and the behavior of particles in accelerators to 16 decimal places. That this same mathematics also predicts the possible existence of closed time-like curves is not a triviality. It is the universe handing us a puzzle whose answer we have not yet found. There is one more thing worth saying, and it concerns not the physics, but the deeper question of what it would mean if backward time travel were possible. If the block universe picture is correct, if past, present, and future all exist simultaneously in a four-dimensional structure, then in some sense everything that will ever happen has already happened. There is no moment of creation for future events. They are simply there, waiting at their coordinates in the block. Your death, whatever it turns out to be, is already fixed at some point in the block. The moment you first understood something important is there, frozen permanently. Every conversation you have ever had still exists in exactly the form it took. This is not a comforting picture necessarily. It removes a certain feeling of openness about the future, but it also means that nothing is ever truly lost. Every person who has ever lived left a permanent imprint in the structure of spacetime, just as solid as any mountain or ocean. The past in the block universe is not gone. It is simply behind you. The way the city you grew up in is still there even when you are far away from it. And if the past is there, if it is a genuine part of the structure of the universe and not just a fading memory, then the question of whether you can get back to it is the same kind of question as whether you can get to a distant star. Hard, possibly impossible with current technology, perhaps impossible in principle, but not ruled out by the mere fact that it is in the past. The past is a place. The question is just whether there is a road. That question remains open, and the people working on it are not dreamers or science fiction writers. They are some of the most careful and rigorous thinkers on the planet, doing mathematics that makes most people's heads swim, drawing conclusions from equations that have never once been wrong about anything they could be tested on. When those same equations suggest that paths through time might be possible, taking that seriously is not gullibility, it is just following the evidence where it goes. We do not know if anyone will ever travel backward through time. We do not know if the chronology protection conjecture will be proven. We do not know what a full theory of quantum gravity will say about closed time-like curves. These are open questions at the edge of human knowledge, and they may stay open for a very long time. But the universe, so far as we can tell, has not closed the door. It has just made it very difficult to find the key.